Hello, my name is Ben,
And my name is Christian.
and today we'll be presenting our EEC 201 Automatic Speaker Recognition Project.
For today's agenda, we're going to go a brief overview of the automatic speaker recognition, ASR. Then we're going to follow up with pre-processing, silence removal, CR analysis, windowing and normalization, then feature extraction, talking about male spectrograms and MFCCs, and training and classification, the LBG algorithm, and finally we're going to show you some results.
Alright, so before we get into pre-processing, I'm just going to give a little background on how ASR systems work. So our objective is to build a text-based system, which means that the system is looking for one key code word. In our case, that's the word 0. And before we get into extracting features from the signal, the process is complicated by the fact that speech signals contain extra information that can interfere with the key information required to do training and classification. So in order to understand this, we actually have to analyze what components of the speaker affect the sound. The main objective of our ASR system is to extract the individual frequency response of each speaker, and each speaker's vocal tract has its own unique response. The other components that are part of human speech are difficult to identify, and they can actually obscure this frequency response that's the most key part for classification. So we group all of the other components into what we call the glottal pulse, and we separate the response of the vocal cords, and we call that the voiced signal. Now we can model this glottal pulse with the voice signal as the actual convolution. Now convolution in time domain is equivalent to multiplication in the frequency domain. So a really important part of this process is to take the logarithm of this multiplication later when we're extracting our MFCCs. But this still isn't a perfect model. It's not a pure convolution. So before this process, we still want to do pre-processing in order to clean up our signal.
So before we train our algorithm, we want to do pre-processing. The first step of pre-processing that we chose to do was windowing. This is better for our signal in frequency domain rather than just straight up truncating it. The Hamming window is one of the most popular windows used, and this is what we decided to go with. But before windowing, we did normalize it so that the maximum amplitude was 1. Our next step in pre-processing was the removal of silence. We did this by looking at the amplitude of the time signal and then leaving out a lot of the silences between and after the signal. Now this still did not get rid of the silences and unvoiced parts within the signal, so we had to move on with another type of algorithm. This led us to researching and discovering the implementation of zero crossing rate. So the zero crossing rate is basically breaking up the signal into a bunch of batches in which we'll find the amount of times it crosses 0, or the rate at which it does. With this knowledge, we're able to calculate the ZCR threshold and determine which frames are actually important. The higher the ZCR, the less important information it is, as well as more likely the noise is within that batch. So looking at the brief snippet of code, we'll actually show this live later. Basically, we're breaking the code up into batches, and then within each batch we're iterating and seeing at every sample point if the previous and next sample point crosses 0. If so, then we add the counter to 1. By the end, we have a total batch count for each window taken. As one of our prerequisites, we were able to add noise to our signal, and then here we're showing pictures of before the signal was processed, so just the raw sound file. Here we're adding a bit of noise. I think the SNR rate is 30 dBs, and you can see it's a little busier here. And then after our first amplitude truncation, we're able to get a pretty clean time signal. And from there, ZCR takes care of the effects a little bit on the outside, but also relieving some of the samples that are not needed.
Now that we've finished pre-processing our data, we can do a better job at extracting the formants. Now the formants are the key timbres that are individual to each speaker, and this is necessary to start building training and testing codebooks through our LBG algorithm, which we'll go over later. Now, one of the more well-known feature sets used in this type of extraction of formants is called the MFCC feature set, which stands for Mel Frequency Cepstrum Coefficients. Now we'll discuss the theory and implementation of these. Looking at the pictures, this takes us through the time domain representation of the signal after processing, the spectrogram of the signal, and the MFCCs. And as you can see, through each step, we're reducing the amount of information required for training. The reason we use MFCCs is that human hearing doesn't operate on a linear scale. Now we hear pitches on a logarithmic scale because the note A4 is 440 Hz, whereas an octave up, A5, is 880 Hz. And although it's not equivalent to this pitch frequency scale that we use, the Mel scale is another way to represent frequency in a way that's linearly perceptual to us. Here's an example of how our hearing isn't linear. This is the frequency response to the human ear, and as you can see, certain frequencies are boosted and certain frequencies are also attenuated. Now the Mel filter bank is the reason why we use the Mel scale. When we multiply a Mel filter bank to a speaker's spectrogram, we can make the formants even more unique, leading to more distinction during the training and the classification phase. Now if we look at the Mel scale filter bank on the top right, you can see that it looks roughly linear below 1 kHz and it becomes logarithmic above that frequency. But in fact, each of the peaks of the Mel filter bank are linearly spaced according to the Mel scale. Now the number of Mel bands we choose for our filter bank can be anywhere from 20 to 120, but for us we found that we had the best success with 35. Now this is our code for extracting the Mel spectrogram, which we need to get our MFCCs. We chose a frame size of 256 and 35 Mel bands as we discussed previously. And given the length of the audio being around 1 second, we get 20 milliseconds per frame, which is adequate for extracting features. So after we take the STFT of our signal, we go ahead and convert it to a periodogram by taking the amplitude squared and dividing by the frame size. Now we convolve that signal with the Mel filter banks, and we're able to extract the Mel spectrogram. Now with the Mel frequency spectrogram extracted, we can further extract the MFCC matrix. The MFCC stands for Mel frequency cepstral coefficients, and the definition of a cepstrum is the inverse Fourier transform of the logarithm of the signal's phase unwrapped spectrum. Now the logarithm is an important step because it removes the glottal pulse from the vocal tract frequency response. And on the right we have a flowchart showing this process. We take the DFT and the log amplitude spectrum, which gave us our Mel frequency spectrogram, and then we take the discrete cosine transform of this. We'll discuss why this is a good choice of transform later, and this leads to extraction of MFCCs. Each speaker's Mel frequency cepstral coefficient matrix is a concise representation of his or her individual formants that can be more easily utilized in the clustering process and classification. Now the log scaling, like we mentioned, is used to separate the voice from the glottal pulse, and in addition to this, we remove the 0th MFCC from the matrix because this represents the mean signal energy, which doesn't change much between speakers, so we remove this for better identification. Now typically we truncate to the first 12 MFCC values, and this is because type 2 discrete cosine transform actually centers energy to the early coefficients. So if we go ahead and remove the later coefficients, this can improve processing speed. Now with these MFCCs truncated to the first 12, we can directly form a code word or ID for each speaker. These are then appended to form a training codebook or dictionary that can be used in the testing phase. This is a brief overview of our code for generating the MFCCs. Once we have the Mel spectrogram and the log of that, we find its cepstrum by taking the DCT. And as you can see, for two different speakers, their MFCCs show clear differences. Now that we have our MFCC vectors for each speaker, we can form a codebook containing the locations or clusters in n-dimensional space, which for us is 12, that best represents the distribution of our MFCCs. Now to form these centroids for each speaker, we use the LBG algorithm, which is an iterative approach to k-means clustering. And on the right, you can see the process of the LBG algorithm that we implemented in our code. Now first I'll go over k-means clustering because this is necessary to understand the LBG algorithm. In k-means, we choose k arbitrary clusters to represent the feature space X, which can be a random assignment or based off of the mean distance averaged to all of the points. Now, this is important that we choose k because this number never changes in normal k-means. Now, we classify the points by assigning them to their closest centroids, and then once we've made the assignments, we correct the locations of the centroids by remapping the centroids to the mean Euclidean center of the data points now classified as being members of these clusters. So basically, once we assign points to the clusters, we remove the clusters so that they better fit the data assigned. And after this, we compute the mean distance from the points to the new cluster centers, and if the terminating threshold or the mean distance is met, then we abort the algorithm, or else we repeat and continue to move centroids.
So for the LBG algorithm, the difference is we're actually using k-means in a way, but in terms of our starting centroid, we're actually selecting an initial point, and then from there we're iterating to find the best points or clusters. We are adding and subtracting a plus delta of 0.01, and based on that, it'll split the centroids. This is the most efficient way in terms of finding the most optimal clusters. So here we can see it's a little snippet of our algorithm, but we have our initializations as previously mentioned. Epsilon is 0.01. We're starting with our initial clusters, and then for every time we want to iterate, we're going to go through and then split the clusters into two, and then from there we're going to decide if it reaches our threshold or if the distance calculated works with our cluster count, then it will terminate. And here's a picture of one of our clusters. You can see that there are 16 centroids, each having different vector quantizations amongst the other points. And then now with those centroids, we're going to actually mix and match them to what we call a code book, in which we'll compare that with the speaker we are testing. This will allow us to decide which speaker is actually speaking using our decision thresholds calculator. We'll show it in our code. Here's a little snippet of our codebook comparisons. We're basically iterating and through all our files, and we're calculating the deviation between the codebook and then the speaker. And then once we find the deviation, we say, okay, is this smaller than the previous one? And if it is, we're going to output, all right, the new speaker is this iteration, which corresponds to the corrected speaker. Our general accuracy playing around with these results was about 12 out of 14, so like 87% in that range. Note we added a couple more speakers, as well as accurate in terms of saying or identifying which speakers have not been trained with. And now time for live testing. Hey guys, so we're just going to go over the code real quick and run some tests. So we're going to run through our main, which is TooB or not TooB, and this is involving no noise and no notch filters. So let's just run it. As you can see, it prints out the test speaker, match speaker, and deviation. You can see right here we have 12 out of 14. Number 8 and number 13 we were having a little trouble with. It also correctly displays when there's not a speaker identification. Now running it through our Melfi own, function is basically calculating the MCC coefficients in which we'll be using to create our codebooks. Note that once we have our codebooks trained, we'll be training the algorithm. So let's add some noise. Some noise sections right here. Let's add it. I believe our threshold was about SNR dB of 35. This is taking into account we're taking the SNR value or desired SNR value to be average power over average noise signal. and let's run it with that. So you can see the threshold right here. It gets most of them right. I believe we are 1 off from the original. So that's probably like 80%. And yeah, so very close. Our threshold is around there. It randomizes it. For sure above 40 dB, we're okay in terms of SNR. So moving forward, we just change that to 40 right now. We have our notch filter testing. We can actually test both of them. We'll uncomment this and then run it. So with notch filtering in the 45 to 50 hertz, we actually only end up getting 10 out of 14 versus 12 out of 14. Reason being is there's a lot of key information in these lower frequencies. However, when we test a little bit higher and larger bandwidth in the upper frequencies, let's uncomment this and comment that. We're trying a notch filter centered at 1500 hertz. The normal human voice range is around, or that we hear is around 80 to like 200 hertz. So this will not affect our results. 1 second, guys. Oh, common. Cool. As you can see here, none of our results have been messed up. Still 87% accurate. Cool. Takes a little longer. Really quickly, before we end, I wanted to go over some of the things we did. As we said, normalization. Method 1 would be truncating, and then we would go into our ZER methods, in which we would plot that out. Extracting STFT matrix, generating MFCs, and then we return the code books. Now, what we didn't get to talk about in the earlier part of this video was the training. So once we have the code books, they'll be coming into this function, and then basically we'll have a huge amount of, or however many code books there are for training, and then we're going to store them in a ultimate code book or code series, in which case we'll store right here. That will be called upon prediction, in which we will go through collecting the speaker codebook, decision threshold, and comparing it with the codebooks that we had calculated previously. And then we're printing out the results. So yeah, that's pretty much it.